In this episode, we will study the basics of finite difference method. In numerical analysis, finite difference method is used to approximate derivative, and while doing computer programming, we use the finite difference method. Let us consider 3 points on the x-axis separated by distance h as shown in the figure 1.1, and we consider 3 points I plus 1 and I minus 1, and now consider another function u, which is a function of x and y, and the value of this function at these points are, in these points ui minus 1, here is ui, and this is ui plus 1. And now we want to do a Taylor series expansion about this point I as follows. Just remember your Taylor series expansion. You know some point x0, which is x0, and there is a small h f x that we know, which is f x naught plus the second term is some h multiplied by the derivative of the function computed at point x naught, and the third term is h square by 2 factorial f double prime double derivative x naught and dot 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 up to infinity. We apply this Taylor series expansion here, ui minus 1 about point I, and that means ui minus 1 ui minus del u del x computed at I multiplied by h del 2 u del x2 computed at I h square by 2 factorial minus del cube u del x cube h cube by 3 factorial del 4 u del x4 h4 4 factorial higher order terms, and it goes up to infinity. And similarly for ui minus 1, that means basically h distance forward direction, h distance backward direction with respect to I points, ui plus 1 ui del u del x I h and dot dot dot, and the similar pattern, and all the terms are positive here minus plus minus plus in this way. And we have to first approximate the first derivative in two different ways. First way is solving du dt from the equation 2 1.2 rather. That means from this equation we can write del u del x computed at point I, which is I plus 1 minus ui divided by this h, this h, and the rest of the term is there. That means minus 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 all the terms up to infinity. And del u del x, I am just truncating it here, and I am just neglecting all the terms. The first term that is neglected, that is h, then h square, higher order term, that means h is a small quantity, so square terms are much more smaller. The first quantity that is neglected, that is h, that is order h. If some term that is h to the power n that is neglected, then that is denoted as something like that. Here the first order term is neglected, that's why OH, and all the terms are clubbed here OH. This is a 2 point. If we consider only this part, only this part of this, then it is called the first order 2 point forward difference approximation of first order derivative of order h, that means first order approximation. It is clearly evident from this expression that if the step size decreases, the error term is reduced proportionally, and therefore that means 2 point forward difference approximation can be written as this: ui plus 1 minus ui divided by h, and we are neglecting this term while implementing in computer or in paper while doing numerical calculation. That should be borne in mind. And I am just written, this is my equation 1.1 and this is my equation 1.2, and the first equation 1.1, this can be written in this way: ui, the second term is minus del u del x computed at point I multiplied by, and rest of the term can be clubbed as this sum formula. If we expand this, you will get all the higher order terms there, and therefore del u del x, you will solve this, then it will imply del u del x computed at I ui minus 1 divided by h, and the rest of the similar fashion first order term and higher order term. This is a first order accurate. This is a first order accurate, and this is called the backward because ui minus 1 divided by your h. That is called 2-point backward difference approximation. Del u del x computed at point I, ui minus 1 divided by h plus higher order terms. And we come back to this diagram later on. Now, if we subtract ui minus 1 and this is my equation 1.1 and this is my equation 1.2. If we subtract this, then from ui plus 1 to ui minus 1 this way, and you will get definitely this will be a minus sign here and all that, and you will get to del u del x I multiplied by h del cube u. This term will cancel out, square term and cubic term will be there, and all that higher order terms. The first order derivative can be approximated as ui plus 1, this can be written as ui plus 1 minus ui minus 1 divided by 2h, this 2 and h, and that is del u del x, del cube u del x cube, and h square term a higher order term. If we neglect these terms and the remaining terms, this is a second order accurate up to. Okay, I am neglecting this term. First, there is no first order term. Therefore, this is a central difference. You are computing the derivative at the point I, and you have to use ui plus 1 minus ui. So we can write, this is called the 2-point central difference approximation, and we can write del u del x computed at point I, ui plus 1 minus ui minus 1 by 2h O of h square. This should be remembered. This is the second order accurate FD approximation of first order derivative. Now, I are going to discuss how to compute the second order derivative. That is, second order derivative is, I am just adding these two equations. If we add these two equations, the cubic term will not there, and all that higher order and all that, and the first order term will neglect, and therefore ui plus 1 plus ui minus 1, that is equals to 2 twice of ui del 2u del x 2, and there is a 2 factorial, so there is 2 cancels out, h square and all that. And therefore, the second order derivative can be approximated as ui plus 1 u minus 2 ui and ui minus 1, that is equals to del 2u del x2 del 4 and all the higher order terms. And I am neglecting dropping this term, therefore the second order term is dropping, so it is second order accurate, and that means del 2u del x2 computed at point I, which is ui plus 1 twice of the central point and the backward point ui minus 1 divided by h square. This is called the 3-point central difference approximation of the second order derivative, which is correct up to second order. This is called 3-point central difference approximation. Let us understand the derivative, second derivative, as well as the 3 types of first derivative visually. This is a visual diagram. I am computing the derivative at this point ui of this del u del x at point I. I am computing this. In order to compute, you need ui plus 1, the value of the function, this is u function, value of the function at this point, forward point, minus ui, the point where you are calculating the derivative, divided by the distance. This distance is h. And here you are computing the derivative here. You need the value of the function at the backward point, that is some distance apart, h distance apart, ui minus ui minus 1 divided by h, and this is a first order accurate. And if you want to calculate according to the central difference, the first order derivative, that is del u del x ui plus, this is ui minus 1, this is ui plus 1, this is your ui, and this is h, this distance is h. Therefore, this is a first order derivative and ui plus 1 minus ui minus 1 divided by 2h, this distance. And this is also second order accurate. This is the first derivative, second order accurate. This is a backward difference. This is a backward difference 2 point. This is a 2 point forward difference. It should be remembered, this formula, and as well as the central difference formula for the second order derivative. That is similarly, that is your formula ui plus 1 minus 2 ui plus ui minus 1 divided by h square. Here ends this episode.